Hey everyone, Mrs. Basega here, and this is the Unit 2 review. Remember, you don't need to watch this whole video. What you should do is complete the review activity with 40 questions. Check your work against the key once you hit submit, and then only watch the parts that you are stuck on. So let's get started. For number 1, we want to graph a velocity versus time graph. And if you have trouble with these, what I suggest is make yourself a T-chart. So on one hand we have Batman, and on the other we have Robin. Batman starts at rest, and he accelerates with a rate of 2 meters per second every second. So that at 1 second, he's traveling 2 meters per second, so on and so forth until he reaches a top speed of 8. So that takes him 4 seconds to do. But once he reaches that 8 meters per second, it says he then travels at constant speed. So at 5 seconds, he's traveling at 8 meters per second, and so on and so forth. Robin, on the other hand, Robin starts at rest as well, but only accelerates at 1 meter per second. So for each second of time that passes, he goes 1 meter per second faster, all the way up to 12 meters per second. After that, he runs at constant velocity too. Notice for both runners, Batman and Robin, you have a section where they accelerate, but then a section where they travel at constant velocity. So my graphs for this are greatly helped by doing this workout for the T-chart ahead of time. When I then use the straight line tool to draw for Batman, he accelerates to 0, 0, to 1, 2, to 2, 4. Batman takes 4 seconds to get to 8 meters per second, then travels at constant speed for the rest of the time. Robin, however, has a lower slope. At 1 second of time, he's traveling at 1 meter per second. At 2 seconds of time, he's traveling at 2 meters per second, all the way up to point 1212. At 12 seconds, he's finally reached his top speed, and then travels at constant after. If I were handing this in for the test, I would make sure to put in who is who. Robin in pink, Batman in blue. So who is ahead at time equals 8 seconds? Well, the word ahead implies area under a curve. We're trying to figure out who ran the farther distance at t equals 8 seconds. So if we zoom in here, Batman has traveled this distance, and I could take the area. But I can see right off the bat that Robin ran less distance. His area under the curve is only this triangle shape. So Batman traveled farther in the first 8 seconds, even though they're both traveling at constant velocity at time equals 8 seconds. So for number 2, Batman is ahead because Batman has a larger area under the curve, which represents distance, than Robin. Now, if I want to calculate the area under the curve for distance, then I would show my work. So let's look at the whole shape that Batman runs. In the first 4 seconds, he travels to a top speed of 8 meters per second. Then he keeps this speed of 8 meters per second from 4 seconds to 20. If I were taking the area of this shape then, the base from 4 to 20 would be a base of 16 with a height of 8. Taking the area of both of these shapes then, it'd be 1/2 base height for the triangle plus base height for the rectangle. That's 1/2 4 times 8 for the triangle, plus 16 times 8 for the rectangle. And that gets us 144 meters. Batman's distance would be calculated using area under the curve, would be 144 meters. You get some of the points for writing in this number, 144. This 2 over here indicates that it's worth 2 points though, The second point is for showing your work. So what I'm going to do is I'm going to click Show Your Work, take a picture of this work, go to Upload Picture, and Add Image. If you're on your iPad and you want to do this by just drawing it on your iPad, you can totally do that as well. Next, for number 5, Batman accelerates, reaching his top speed of 8 at 4 seconds of time. Then he runs with constant velocity. I see that he has a positive acceleration to start, and then constant. So I would expect his position versus time graph for the same period of time to be an upward facing curve for positive acceleration for the first 4 seconds, then some sort of straight line, some sort of constant velocity. So which graph matches that? I think D does. That shows an upward facing curve corresponding to positive acceleration, and then a straight line for positive velocity. So for my reasons then, when accelerating, the position versus time is an upward facing curve. When traveling with constant velocity, the position versus time graph is a straight line with a slope. If you're having trouble telling these two apart, it's not a horizontal line because that would mean an object that is staying in the same position. With a slope indicates that it is traveling. Number 7. Lazaro Schaller completes the world's highest high dive, and he's in the air for 3.5 seconds. Assume free fall conditions. What free fall means is that for every second of time that passes, his velocity becomes more negative, becomes 9.8 more negative. So I can fill this out right here. After the first moment, he's traveling negative 9.8 meters per second, then negative 19.6, then negative 29.4. I'm just repeatedly doing our 9.8, subtracting 9.8 repeatedly for every second of time that passes. Okay, so what do I do if only half a second of time passes? Well, then instead of subtracting 9.8, I'm only subtracting 4.9. So on my calculator, 9.8 divided by 2 means that in half a second of time, the speed changes by 4.9 instead of 9.8. So what I'm going to do is I'm going to do 29.4 minus 4.9, and I see a final velocity of negative 34. For his velocity as he enters the water, even if you filled out your T-chart wrong, you should know it's a negative number. You should know it is not 0. We know it's not 9.8 because more than 1 second of time has passed. It's certainly not 2.8 because then that would mean less than a second of time has passed. It must be B. If air resistance were taken into account, that would make his final speed slower. So now let's do the velocity versus time graph using our T-chart from number 7. I want to plot a straight line that starts at 0, 0, and at 3.5 seconds of negative 34.3. The nice thing is, I don't need to plot individual points because this is a straight line. So use the straight line tool, start from 0, 0, and the velocity goes to negative 34.3 in 3.5 seconds. Now, to calculate the height of his dive, I want to use area under the curve of this shape. So maybe for show my work, I show it over here. This is a triangle that started at 0, 0, and after 3.5 seconds was at a final speed of negative 34.3. So the height of this triangle is negative 34.3, and it took 3.5 seconds. The area under the curve always gives us height, depth, length, anything measured in meters. So I'm going to do area of 1/2 base height, with a base of 3.5 seconds and a height of negative 34.3 meters per second. This gives me an area under the curve of negative 60.025. Right here, I'm going to round this. Negative 60.025 is like negative 60. For show your work, I'm going to take a picture again. This shows me that you've used area under the curve. I now know that you know how to calculate distance from a graph. Okay, but what if you had an object that instead of starting from rest and falling down, getting faster and faster and faster, what if you had an object whose initial velocity was positive? If you're having trouble picturing this in the back of your head, imagine an object that is moving fast and up. It slows down as it reaches the apex, stops, and then turns around, accelerating back towards the planet. So I would want a positive velocity to start and a negative velocity at the end. At the apex, the velocity would be 0. So I see 3 data points already. I know that in this t-chart, at t equals 2 seconds, the velocity is 0. Now let's use this negative 9.8 repeatedly to find the other velocities. For every second of time that passes, we subtracted 9.8. Well, that means the second before the apex, you would have been traveling positive 9.8 meters per second. The second before that, you would have been traveling positive 19.6. The second after, you'd be traveling at negative 9.8 and negative 19.6, and that would represent where you're falling down. So the first 2 seconds are during this rising motion. You start with a positive velocity of 19.6 and go to rest in 2 seconds. By 4 seconds, you're now traveling negative 19.6 because you decelerated back down to the planet for 2 more seconds. This line should look really similar to the line you just had for free fall. A free fall graph of velocity versus time will always have a negative slope. This comes from the fact that the acceleration due to gravity is the same for all objects. For each moment of time that passes, you subtract 9.8 meters per second so that we can figure out the velocity at any point in time. Under show your work, to make this neat then, I'm going to choose the straight line tool. I'm going to start at just under 20, make sure I hit 2 seconds to be the apex, and go to negative just about 20 for a graph that uses a nice straight line. Now, this free body diagram is actually easier than you think. At t equals 1 second, your object is still in midair. It's not touching your hand. It's not being hit by the floor. We're always doing no air resistance because free fall. So what is the only force acting on the object if there's no normal, no drag, no air resistance, no tension? Then the only force acting on this object is gravity. Not a trick question. For number 15, let's sort each item. The acceleration at all of these points is negative 9.8. That includes at the apex. Why does it include at the apex? For a few different reasons. See how at the apex the slope is still negative? That means the acceleration is still negative. Gravity is the only force acting on it, even at the apex. So it is still in free fall at the apex, and the acceleration is still negative 9.8. You'll notice on the t-chart too, 2 seconds, you were still subtracting the 9.8 repeatedly, so the acceleration was still negative 9.8. The initial velocity was positive 19.6 because that's where you were traveling upward. The final velocity when it was just about to hit the ground was negative 19.6 because it was traveling down, and the velocity at the apex was 0. If the mass of the toy rocket doubled, the acceleration due to gravity would still be 9.8. The reason it's still 9.8 is because, well, all objects fall at the same rate, no matter their mass. Thinking of this in terms of Newton's second law might help. The free body diagram for an object in free fall is just Fg. Newton's second law says that acceleration is caused by a net force acting on a mass. But the only force acting on here is gravity. So I'm going to put mg, the weight, the force due to gravity, as the net force. It acts on the mass. When you double the mass, you also double the weight. It doubles the inertia and makes it harder to move at the same time you're pushing it harder. So the mass doesn't matter for acceleration in free fall. This is why all objects fall at the same rate. The ratio of mass to weight stays the same. Now, talking about weight, how do you in general calculate weight? Is by doing Fg equals mg. This is a 90 kilogram couch. The fact that she's pushing on it doesn't change its mass. Since weight only depends on mass, I could write Fg equals mg. That's 90 kilograms times 9.8, and that gives me 882 newtons. And that means you get 1 point for showing your work and 1 point for the answer. You don't need to include the n for newtons here because it's grading this numerically, so do you have the correct number? So for free body diagram, she pushes the couch at constant velocity. Constant velocity means equilibrium. That means the normal force that pushes upwards has to cancel the weight that pushes downwards. Her applied force to the left has to equal friction force to the right. So I want to make sure to draw these lines proportionally on the grid and then label each force, including the numbers if we know it. Number 19 is about equilibrium. Normal and gravity are the y direction equilibrium. Friction and applied are the x direction equilibrium. And it doesn't mean that they all have the same magnitude as each other. It just means that left cancels right, so both are 600. Up cancels down, so both are 882. Doubling the mass would double the normal force. So that would actually change the friction force. If you doubled the weight, then you also doubled the normal force, and that would make friction bigger, right? Imagine pushing a couch with someone on it versus someone off of it. Because their weight increases the weight of the couch, the normal force would increase. That pushes the two surfaces together harder. So more normal, more friction. But doubling the normal force doesn't change the coefficient. This coefficient of friction, its symbol is mu for material. If I double the normal force, does that change what the couch is made of? No. The coefficient of friction stays the same. What does surface area have to do with this? Actually, nothing. Since surface area isn't in this equation, no matter what I do to surface area, the force of friction doesn't change. Oh, but 23. What if I replace the material with a very low friction plastic? If mu decreases, then friction decreases. So if I put a more slippery material, the friction force will decrease. All in all, if I want to make friction lower, I can make it a smoother material. That would lower mu. I could add oil or lubrication, and that would lower mu. I could put less normal force by taking some mass off of the sofa. If someone was no longer sitting on it, a smaller mass would mean a smaller weight, would mean a smaller normal force, which would mean a smaller friction force. For number 24, we're trying to figure out this graph. When you put an applied force of 3, that is the maximum amount of friction that you can have without it starting to move. This is called the threshold of motion. So 3 newtons is the minimum amount of force required to start an object moving. If you only put in 1 newton, that doesn't make it over the threshold, so you would stay in static equilibrium. If you put in 4 newtons, though, this object would accelerate. Even though this line is flat, I want you to think of it like this. You put in 4 newtons of applied force, so Fa is 4. Friction was only 2, so go from 4 over to the left, or actually it's 1.5. My friction force is 1.5. For kinetic friction, the net force is to the right, so the acceleration is to the right. How do we get the net force here? I would be doing net force is equal to force right minus force left. Or in this case, 4 minus 1.5. This leaves a net force of 2.5 newtons. But I don't need to include the n for newtons. I've got my 1 point for the work. Now this is just grading the number. If the net force is 2.5, then the acceleration be calculated with Newton's second law. Newton's second law says that acceleration is caused by net force acting on a mass. The net force was 2.5 newtons to the right because it was more right than left, and I subtracted those. And the mass is a mass of 2 kilograms. And 2.5 divided by 2 gives me an acceleration. That acceleration is 1.25 meters per second squared to the right. But I've already got my show your work point because I put the equation already. So I only need to include the 1.25 here with no units. Please do note, though, that for showing your work, it's not enough to just write 2.5 over 2. You have to write F net divided by m first. For number 28, the block in the table have a coefficient of friction that is actually already quite small, 0.077. In order to have less friction, I'm looking for a coefficient that is less than that. So this is 0.077, or 77 thousandths. Okay, so it can't be 300 thousandths. So it's not wood and wood. It's steel and ice. Notice that 0.05 is less than 0.077. So lowering the coefficient makes it a smoother material, so lower friction force. Now for number 29, you and I did an experiment like this already. In this one, the control variable must be mass, because the mass is unchanging. They change the force and measure the resulting acceleration. When the force doubles from 10 to 20, the acceleration also doubles from 1.42 to 2.91. Or I can look at the other point. I can look at when it doubles from 20 to 40, the acceleration doubles from 2.91 to 5.71. So doubling the force doubles the acceleration. That makes sense to me because I know force and mass. Because I know force and acceleration have a direct relationship. If we push harder, an object accelerates more. So net force was the independent variable. That's what you changed in the experiment. Your changing net force created an acceleration. And in the trials, mass all stayed the same. This experiment was trying to find the relationship between force and acceleration. This was a linear dependence because if I push harder, the acceleration increases. So I'm going to drag this over to box 1. But the other half of Newton's law is that mass and acceleration are an inverse relationship. So I'm going to drag the dependence of acceleration on mass to the third graph picture. If mass increased, I would expect less net force. So if this experiment were repeated with a larger mass, I would expect smaller accelerations. All right, let's say we have a luge competition, and we have a frictionless, dragless, theoretical Olympian, and we want to show the free body diagram. This little dotted line is there to show where the ramp angle is. We know that gravity points straight down, but the dotted line is there so you can draw normal force correctly. Normal force should be perpendicular and smaller than the weight. The reason your Olympian travels down and to the right is because the normal force is pointed to the right and is smaller than gravity. Because it's smaller than gravity, the person accelerates downward, and because it has this x component, it travels partially to the right. Be careful not to add extra forces here because it said really specifically that friction and drag weren't part of this. If you tend to draw free body diagrams and you're a little bit messy, these 90-degree marks so that I can clearly see that normal is perpendicular to the ramp. Next, we have another weight question. Weight is the product of mass times the gravitational field that the object is in. So if it's an 80 kilogram competitor, I would be doing 80 times 9.8, and this gets 784 newtons. I get 1 point for the equation, but again, I'm going to point out that the equation I'm talking about is this one. You get a point for the Fg equals mg equation, not the 80 times 9.8. So always show your work using the equation from the equation sheet. So I got 1 point for show my work, 784, done. Now if I made that angle steeper, I would expect the acceleration to increase. The weight would stay the same though. Is it still an 80 kilogram person? Yup. Are they still near the surface of the earth? Yup. So the weight would stay the same. And that must mean the normal force decreases. On a ramp, your normal force is smaller than your weight, so making it a steeper ramp must make the normal force even smaller. Now, let's say that the bobsledder wants to control their velocity. They could do air resistance, and air resistance depends on surface area, shape, size, and surface material, right? A smooth car would have less air resistance than if you had like a car covered in fabric for some reason. So for air resistance, I think of the 4 S's: size, shape, surface area, surface material. Friction is the one that depends on coefficient and normal force. Don't get those confused. If I wanted to make friction larger then, I could change the material to have a larger coefficient, or change the normal force somehow. There's actually a lot of different options here. I could make the coefficient larger, because that would increase the friction force. If I wanted to write that as a rougher surface, because that would make the coefficient larger, you could write that as well. You could say something like increase normal force. But increasing the normal force could be accomplished by increasing the weight. Finally, the last problem is a calculation problem. Including friction and drag, the acceleration is 3 meters per second squared. Their initial velocity is 4 meters per second. So how fast are they traveling after 6 seconds? I'm going to show you 2 different ways for this. In the problem, it says there's an initial velocity of 4. And for every second of time that passes, it goes 3 meters per second faster. I could do this by repeated addition. 4 plus 3 is 7. 7 plus 3 is 10. 10 plus 3 is 13. 13 plus 3 is 16, 16 plus 3 is 19, and 19 plus 3 is 21. Alternatively, that says acceleration is the change in velocity over time. The acceleration was 3. We're trying to find the final velocity. The initial velocity was 4, and the time is 6. So 6 times 3 is 18. VF minus 4, so to get rid of a minus, I would add this to the other side. VF would equal 18 plus 4, or 22 meters. In either case, notice that it gets you to the same answer. The 6-second velocity is 22 meters per second, whether we do it as an equation or a T-chart. And that's all, folks. Best of luck on your test.